Welcome to my YouTube channel Modi Mechanical Engineering Tutorials. In this video I would like to explaining about two metals which will be completely soluble into liquid state and completely insoluble into solid state. So that will be nothing but Eutectic type of transformation. So in this video I would like to take an example of cadmium and bismuth. So let's take a melting point of the cadmium and bismuth. So cadmium having a melting point around 321 degrees centigrade, bismuth having a melting point around 271 degrees centigrade. And for the eutectic type of transformation, eutectic compositions, and that will be 40% of CD, or you can say cadmium, and 60% of bismuth. And for the eutectic temperature, so that will be around 144 degree centigrade. So this is the conditions for the eutectic transformations. So now let's see for making a phase diagram for cadmium and bismuth, which will be having a eutectic type of transformations. So here this is x-axis and y-axis. So for the making a phase diagram, let's make a x-axis as a weight percentage of composition, and onto the y-axis that will be the temperature in degree centigrade. Now onto the x-axis, I would like to take several points of the different weight percentage of the cadmium and bismuth. So let's start here with the weight percentage of bismuth and weight percentage of cadmium. So starting with the 100%, so 100% of the bismuth with 0% of the cadmiums. And onto the another side, here it will be the 0% of the bismuth with 100% of the cadmium. And these all are the points like this: 90-10, 80-20, 70-30, 60-40, 50-50, and go on. Now onto the y-axis, that will be the temperature in degree centigrades, and according to the given range of the temperature as a melting point for the cadmium and bismuth. So here the maximum temperature of cadmium, and that will be the 321. So let's talk on a scale onto the temperature axis. So 100, 200, 300 and 400. Now from the given conditions as a cadmium, that will be having a 321 centigrades as a melting point. So let's take a side which will be having a 100% of the cadmium. So this point. So just you can make a point at 321. So here that will be the 300 point. So just above this point. So it will be noted as a 321 degree centigrade. Similarly from left side, so here it will be the bismuth having a melting point 271 degree centigrades. So just take a side at 100% of the bismuth, so here, and 271. So I think it will be almost here 271 degree centigrades. Now there will be the eutectic conditions as the eutectic compositions and eutectic temperature. So eutectic compositions, 40% of the cadmium. So just you can say this will be the side of the cadmium, so 40%. So just you can make a point as a eutectic compositions. And the temperature, or you can say eutectic temperature, so that will be 144. So I think it will be almost over here, 144 degree centigrade. So that will be nothing but eutectic temperature. Now eutectic means our liquid phase of cadmium and bismuth that will be converting into the two different solids. So here it will be the solid 1 plus solid 2. But where? At eutectic temperature and specified at eutectic compositions. So this 100% liquid that will be solidified under the cooling into two different solids. So in the reverse case, if you heat these two solids by the heating process, so once again it will be converting into liquid. So this is the conditions of eutectic, means single phase of the liquid that will be transferring into the two different solid. So this point, or you can say these reactions, it will be known as a eutectic reactions, and specified this temperature, or you can say eutectic temperature and eutectic compositions, it will be intersecting at one point, and that will be representing as a eutectic points. So let's plotting for the eutectic points according to the given conditions of the eutectic composition and eutectic temperature. So from 60% of bismuth and 40% of cadmium, so that will be nothing but eutectic compositions. So you will make a one vertical line, and from the temperature, or you can say at eutectic temperature, make one horizontal line. So by the making a one vertical line and horizontal line, so it will be intersecting at this point. So this point is known as a eutectic point. So now it will be making a 3 points, one onto the 100% at bismuth. So here that will be the P point. At eutectic point it will be Q, and 100% of the cadmium, that will be around 321 as a R point. Now according to the eutectic transformation, I would like to join P, Q and R. So into the eutectic phase diagram, this line P, Q and R, it will be representing as a Liquidus line. Now there will be some more points like S and T. So just you can see the line which will be P, S, Q, T and R. So that will be representing as a solidus line. So as from the definition of the Liquidus line, all the above portion of the Liquidus line, that will be act as a 100% liquid, because into the liquid phase both the metals cadmium and bismuth, that will be completely soluble. And for the solidus line, just below the solidus line, it will be the formation of the two solids. So here it will be the solid number 1 plus solid number 2, because both the metal cadmium and bismuth, that will be completely insoluble into solid state. Now I will take a case number 1. So for case number 1, that will be the transformation which is passes through the eutectic points. So let's take a different points onto the eutectic transformation line. A, Q, that will be itself as a eutectic point, and B point, that will be at a room temperature. Now I would like to draw a microstructure for these three different points. So at point A, which will be at above the Liquidus line, so it always forms 100% of the liquid. But here that will be the mixture of cadmium and bismuth. So it will be the total mixture of cadmium and bismuth in the form of liquid phase. So this is a cadmium, and this green, it will be act as a bismuth. How much percentage? So around 60% of Bi and 40% of cadmium. Now I would like to draw a microstructure at point Q. So just you can see at point Q, or you can say at eutectic point. So according to the definition of the eutectic point, all the liquid which will be present just above this line, it will be transforming into two different solids. So at Q point, or you can say at constant temperature, eutectic temperature point, that will be transforming into the two different solids. So first of all, I would like to draw a cooling curve at a eutectic point. So here it will be the 100% liquid, and in between these two regions, so it will be mix liquid plus S1 plus S2, and then after it will be S1 plus S2. So in the simple way, for the binary eutectic system, it will be constant temperature solidification process, but it forms the two different solid, because both the solids that will be insoluble into solid states. So just you can see for the microstructure, so just you can see this orange, that will be the cadmium around 40%, and this green, that will be the bismuth around 60%. So all the liquid of cadmium and bismuth, that will be transforming into two different solid. So now I would like to draw one kind of microstructure at a room temperature. So just you can see for the room temperature, it will be the refinement of the structure, or you can say rearrangement of the structure into the room temperature. So just you can see that will be the cadmium, and this green, it will be act as a bismuth. So at room temperature, it will be making different grains and grain boundaries. So it will be having a grain, and these black lines, it will be grain boundary, and it forms a two different solids for S1 and S2. So basically this S1, it will be refers to a bismuth, and this S2, that will be refers to a cadmium. So just you can note down S1 from bismuth, and this S2, it will be from cadmium. So in the eutectic phase transformation from 100% liquid to the room temperature, so the important part at point number Q, or you can say at eutectic points. So what happens at eutectic point, or you can say at eutectic temperature? First crystals of the one of the components. So generally it will be having a higher melting point. So here the cadmium, which is having a higher melting point, so that's why that will be begins to start as a solidification process. Then the cadmium crystals become a richer into the second components as a bismuth. So now it will be also having a freezing at a same temperature. So for starting of the solidifications, it will be carried out by the metal which will be having a higher melting point. Then other metals which will be also solidified at a same temperature, or you can say it will be the eutectic temperature. So finally at a room temperature, basically for the eutectic compositions solidified at a constant temperature and forms of the bismuth and cadmium side by side in an alternate laminas, that will be called as a eutectic structure. So this eutectic structure only forms if your solidification process, or you can say phase transformation process, it will be passing through the eutectic point. So this transformation, if it will be earlier than the eutectic point, so you can take any point of up to this eutectic transformation line. So that will be known as a hypoeutectic. So just you can note down. So this hypoeutectic, it would be up to the eutectic composition range. And if your transformations which will be take place after the eutectic transformation line. So that will be known as a hypereutectic. So just you can note down. Now I would like to take a second case which will be take place into the hypoeutectic transformations. So case number 2, it will be 90% of bismuth and 10% of cadmium. So just you can make a one vertical line from 90% of bismuth and 10% of the cadmium. So just you can see, after making a one vertical line from this composition line, or you can say the for case number 2, so that will be intersecting at the different lines. So first of all, it will be making an intersecting at a Liquidus line. So I would like to make one point, then that will be making a intersecting at solidus line. So similarly for microstructural view, I would like to make a different points. So first point, that will be just above, so that will be known as a E dash. If it will be intersecting at a Liquidus line, so this point is known as B dash. Then this line which will be intersecting at solidus line, so C dash, and at room temperature, so that will be D dash. So just you can see for the microstructure at point A dash. So here it will be just above the Liquidus lines. So according to the definition of the Liquidus lines, all the above portion of the Liquidus lines, it will be forms 100% liquid of the two metallic compositions. So here it will be the bismuth plus cadmium, and bismuth that will be having a 90%, and cadmium it will be having a 10%, and it will be makes a 100% liquid at point number A dash. Now the important part, it will be around point B dash, or you can say intersecting at Liquidus line. So just you can see into the transformation from the liquid to solid. So first of all, it will be intersecting at Liquidus line. So at Liquidus lines, it will be the starting point of the solidification process. So basically this is the region of the hypoeutectics. So it always follows a off-eutectic kind of transformation as a cooling curve. So first of all, I would like to draw a off-eutectic binary alloy kind of cooling curve. So let us see. So here all the above portion of these Liquidus lines, so it will be makes 100% liquid. So once it touches the Liquidus lines, or you can say that will be the starting point of the solidifications. So after this, it will be making a solid particles, so liquid plus S. So basically it will be S1. So that will be from a cadmium or bismuth. But practically, which kind of metallic elements it will be having a enrichment. So basically that becoming as a S1. So one of the metals it will be start to solidify, and rest of the other metals it will be in the form of liquid. So after these regions, it will be making liquid plus solid. So here either it will be S1 or S2, both having a possibilities. But practically which metal that will be having an enrichment, that metal it will be starting with the solidification process. So from this side, it will be around 90% of the bismuth. So here liquid plus solid as a bismuth. So just you can note down liquid plus bismuth. And once it touches the eutectic temperature line, that means constant temperature solidification process. So up to this C dash point, liquid plus solid one, because one of the metals it will be almost completing its solidification process, and rest of the other, suppose here it will be the bismuth that will be starting with the solidification process. So up to C dash point, almost it will be complete the solidification process. So rest of the other as a cadmium, now it will be in the form of liquid, and this temperature range it will be having a solidification process. So after these points it will be liquid plus S1 plus S2. So up to this point that will be the end point of the solidification process. So after this it forms the two different solids. So here S1 plus S2. So now I would like to make a microstructure at B dash point. So just you can see, so there will be the starting point of the solidifications, or you can say formation of the nuclei. So this nuclei basically that will be made with the bismuth materials at a hypoeutectic transformations, or you can say in simple way enrichment by the metals that will be having a starting point. So the bismuth which will be having a green color codes, so that will be the starting point of the generation of a nuclei. So that will be nuclei, and rest of the others from the bismuth still it will be into the liquid state, and there will be the 100% of the cadmiums still it will be having a liquid phase. So here it will be liquid plus solid. So solid that will be refers to the enrichment by the metals. Now I would like to make a microstructure at point C, or you can say at eutectic temperature. So eutectic temperature means constant temperature solidification process. So it will be mix of two different solids. So at point C dash, just you can see the microstructure. So it will be mix of two different solids of cadmium and bismuth with the enrichment side of a bismuth. So just you can see, so here that will be from bismuth and this one is from cadmium. So now I would like to make a one microstructure at a room temperature. So at room temperature once again it will be mix of two different solid of the cadmium and bismuth, but just you can observe like this, it will be the refinement of a grain structure. So just you can see for the microstructure at point D dash. So here at a room temperature at D dash points, so the 90% of the bismuth is being present, and rest of the others at a 10% of cadmium. Now if you want to find out a weight percentage of the liquid and weight percentage of eutectic of bismuth for a hypoeutectic transformations at certain temperature range with respect to the 90% of bismuth and 10% of cadmium. So here already that will be the one vertical lines. Now suppose into this case, suppose I want to introduce a temperature range. So how much percentage of the liquid is being formed? So that will be calculated by a lever arm rule. So suppose there will be the temperature around 200 degree centigrade. So here it will be the temperature of the 200 degree centigrade. So just you can make a one horizontal line which will be passing through the solidus line, this one composition line and liquidus line. Just you can see, so this line which will be passing through the solidus line, composition line and liquidus lines, it will be known as a tie line. So I would like to make a points here as a x, y and z. So x point that will be intersecting at solidus line, because that will be the solidus line as a P, S, Q, T, R. And here y point that will be intersecting as a composition line. And third point Z, it will be intersecting as a liquidus line. So suppose I want to find a weight percentage of liquid. So just you can see. So in the case of the weight percentage of the liquid, so just you can take a side which having a intersecting of solidus line. So here in this diagram, this x point, it will be the intersecting point as a solidus line. So just you can take a distance from x point to the composition line. So xy divided by total length of tie line. So xz into 100%. Now for finding a xy and xz, so you will take a projections at a composition line. So let's see. So here from z, it will be around 25% of cadmium. So every time I would like to take a reference as a weight percentage of cadmium. So here that will be the 25% of the cadmium, here 10% of the cadmium and 0% of cadmium. So for xy, so 10 minus 0 and here 25 minus 0 into 100. So around 40% of liquid is being present at a point y. Now I would like to calculate the weight percentage of a solid, or you can say weight percentage of the bismuth. So just you can see. So weight percentage of the eutectic bismuth. So there will be the solid particles. So just you can take a intersecting from a liquidus line. So z point. So yz divided by total line. So xz into 100. So for y to z, so that will be 25 minus 10 divided by 25 minus 0 into 100. So that will be almost 60% of bismuth. So at point y, almost 60% of the solid is being formed. So remaining 40% of the liquid is being present. So with the help of lever arm rule, you should find a different kind of percentage of the liquid and eutectic bismuth. So this is the all case regarding for a hypoeutectic transformations. Now I would like to make a one transformation in which will be having a hypereutectic transformation line. So this is the case number 3, which will be having a 30% of bismuth and 70% of cadmium. So just you can see this is the point. So from this composition line, I would like to make a one vertical line which will be representing the transformation line. So just you can see. So here similarly we discussing for hypoeutectic transformation. This is a hypereutectic transformation line. But here the enrichment by the cadmium, which will be having a taking a active role for the starting of the solidification process at the intersecting at Liquidus line. So just you can make different points. Similar we already discussing with hypoeutectic transformation. So here that will be the ASS intersecting of Liquidus, so B double dash. Similarly at eutectic transformation, so C double dash, and at your room temperature, so D double dash. Now I would like to make a microstructure for the different points. So before discussing with the microstructure at the various points, first of all I would like to make a cooling curve for a 30% of bismuth and 70% of cadmium. So just you can see. So just above the Liquidus lines, it always forms 100% liquid. After it touches with the Liquidus lines, so it will be the starting point of the solidifications. So here liquid plus one of the solid. So here solid 2, solid 2 that will be representing as an enrichment of the metals. So from this side, so that will be the enrichment of the cadmium. So this S2 it will be act as a cadmium. So from the hypereutectic transformations, cadmium acts a vital role for the starting of the solidification process. Now from the cooling, or you can say solidification process, it will be touches the eutectic temperature line. So at eutectic temperature line, it will be the constant temperature solidification process. So remaining all the portions which will be converting into the two different solids. So from this region it will be liquid plus solid 1 plus solid 2. So just below of this eutectic temperature line, it forms a two different solids. So in case of the eutectic system, both the metals which will be having a completely insoluble with each other. That's why it will be forms of two different solids. So here S1 for the bismuth and S2 for the cadmium. Now I would like to make a microstructure for A double dash, B double dash, C double dash and D double dash. So let's see. So for A dash, it will be just above the Liquidus line. So it will be makes a 100% liquid of cadmium and bismuth. Just you can see. So that will be the bismuth. Now it will be for cadmium. So here it will be the enrichment by the cadmium. So it will be makes a 100% liquid. Now for B dash. So that will be the starting point of the solidifications by the enrichment by the metal. So here that will be the cadmium. So cadmium representing as a green color. So it will be the starting point of the solidification process. So this is for the at B point. So that will be act as a nuclei. And rest of the other parts from the both the metals which will be in the form of liquid. So this is now for the cadmium. So there will be the starting point as a solidification, so formation of the nuclei and that nuclei having a growth. So now for the microstructure at C point. So there will be the some portions, or you can say one of the metals, it will be completely solidified. So this cadmium which will be 100% solidified, but rest of the others as a cadmiums, now it will be in the form of liquid. So this is in the form of liquid. So this is known as a cadmium, and this orange color it will be bismuth. So after this, or you can say at just below of the eutectic point, so these all the cadmium and bismuth that will be in the form of the solid. So eutectic temperature means it will be the constant temperature solidification process. Now I would like to make a microstructure at a D double dash, or you can say around room temperature. So at room temperature it will be makes two different solid, and that will be S1 and S2. So this is for a metallic phase diagram for a cadmium and bismuth. Similarly, you should also use a lever arm rule for the finding of the weight percentage at the same temperature. Just you can make a tie line with these lines, right? So according to the given data, you will easily draw a phase diagram for cadmium and bismuth. So this is all about the phase diagram of eutectic binary metals of cadmium and bismuth. So if you like this, then subscribe and share more the mechanical engineering tutorials. Thank you so much and keep watching.